So here is the Mathcad calculation. It's only 2 pages, and my convention, as usual, is to highlight the inputs in yellow, and then I put the outputs in a kind of shade of orange as well. And the unshaded text are the calculations from the input. And again, the usual convention is you put descriptions on the left, calculations in the middle, and the references on the right. So we're looking at a flow of calculations from left to right and top to bottom. So we give it an input of the floor span, the floor thickness, and the unit weights, and we had a superimposed dead load. Again, you don't need to put too much in there. The more weight you have in your system, the better in terms of vibration. You work out the Young's modulus, in this case from our own NZS 3101, and you put in the live load. Again, you don't put in the full live load, but a proportion of it. So this is a residential building, and we're looking at about half the normal live load to add to the instantaneous deflection. Now, again, it's a little conservative to look at these floors as simply supported, but it's a simple calculation. So behind that is the simple 5W L to the power 4 divided by 384 E and I. Now, we've increased the E value because you're looking at an instantaneous deflection. And the quicker you apply the load to any structure, the stiffer it suddenly becomes. And from that instantaneous deflection, we can get the natural frequency of this floor as 5.34 hertz. So we're going to use it for walking, first of all. We take in consideration the whole bay. We take an empirical constant of K taken from table 1 of the Mast paper of 58 kilonewtons, and apply an approximate modal damping ratio, in this case 5%. And we get a natural frequency that's required of 4. So is our natural frequency bigger than the required? And happily it is. So we then go on to dancing. I've put the tables in little areas so you can expand or shrink them down as required. So when we're looking at dancing, we take a constant K of 1.3 and carry the acceleration limit from table 2 and the other parameters from table 3. You have a forcing frequency, which is typical with dancing, of 3 hertz. The dynamic coefficient, again, from the table of 0.05. You take a value of the weight of participants, and again, this is much lower than the normal UDL you would apply for a live loading. And then top that all up, put it into the equation to get your minimum natural frequency required for the dancing situation. And as it turns out, that's 3.38 hertz. Is our natural frequency bigger than that? Yes, then it's okay. For mechanical equipment, I haven't written up the calculation for that, so go see the Mast paper.